Now let us begin the topic of indefinite integration by understanding the concept of integral as an antiderivative. Now to begin with, let us consider one example from differentiation. That is, suppose we consider a function say x square and we want to find its derivative. Okay, so if I want to find the derivative of x square, we know that it is 2x. Now the opposite process of differentiation is called as the integration. So if 2x is the derivative of x square, then we call x square as the integral of 2x. So that means the opposite process is what is called as the integration. So this is the symbol of integration. Now there is one important point regarding this definition, that is, just by changing the direction, the function x square does not become the complete integral. For that we have to understand one more point. For that, understand that suppose instead of x square I consider the function as x square plus 1, and if we ask the question what is the derivative of this, now here we know that the derivative is still 2x because the derivative of the constant term 1 is 0. So now in this example, if I ask you that if the derivative of x square plus 1 is 2x, then it means the integral of 2x in this example becomes x square plus 1. So in the first example the integral of 2x was x square. In the second example the integral of 2x was x square plus 1. And it won't be difficult to realize that, suppose even if I had the another example as say x square minus 3, still the derivative is 2x, but whereas if you come back and see the integral, then it is x square minus 3. So in general what we are observing is, suppose we want to take the integral of 2x, then it will be of the form x square plus some constant, right? So we don't know what that constant would be, but definitely there will be some constant in general. So therefore we write this particular fact of integration as follows. We write it as integral of function 2x with respect to x. Okay, so this particular expression dx indicates that we are integrating with respect to x. It is very much similar to what we say as differentiating with respect to x. So similarly here we are integrating with respect to x, and the answer is x square plus some constant c, alright, which we don't know, but there will be definitely some constant, and this is called as the constant of integration. So it is important to note this particular point, that there will always be some constant of integration. Alright, and now here it will be once again clear that the integral is also called as the antiderivative, isn't it? So the other way of looking at the integral is that, suppose whenever we want to find the integral of some function, say here 2x, we are basically asking the question that which is that function whose derivative is 2x, isn't it? So therefore here we realize that that function must be of the form x square plus some constant whose derivative will be definitely 2x. So that is the simplest idea of integral. Now since we know some of the derivatives of standard functions, so based on that, if we revert the process, we can easily see that how we can define the integrals of some of the common functions. So let us see the standard formulae which are based on the results that we already know from differentiation. So we will go through all the simple formulae one by one. First one is integral of x raised to n is given by x raised to n plus 1 whole upon n plus 1. So what do we observe is, whenever we integrate some function in which x is raised to some constant power, then in the answer the degree of x increases by 1, and same is dividing that particular expression. Alright, now a way to check this is that we can differentiate the function which is there on the right hand side, and we will get back the function on left hand side which is getting integrated. Alright, so that is another way. Now second one is integral of 1 upon x is log x, because we know that derivative of log x is 1 upon x. So that's the opposite process that we are following. Then integral of k is kx, because once again derivative of kx is nothing but k, right? And similarly the next two results, that is integral of a raised to x is a raised to x upon log a. That is simply because when you differentiate a raised to x, you have a raised to x multiplied by log a, and hence log a gets cancelled and we are left with only a raised to x. Now the fifth formula is a special case of fourth formula, that is if you put a as e, then the answer will be obviously e raised to x only, because denominator log e is nothing but 1. So moving on, let's see couple of further formulae also. Alright, here we have integral of 1 upon root x, that is nothing but 2 into root of x. Now let us just see the details of this procedure in case it's not clear. As an example, let us see 1 upon root x. So now whenever we have 1 upon root x, if you want to write it as a degree of x, that means as some power of x, then that can be written as x raised to minus half, simply because it's a root and it's in denominator. So therefore 1 upon root x is nothing but x raised to minus half dx. Now we have already seen a result that if we have the function of the form x raised to n, then its integral is given by x raised to n plus 1 upon n plus 1. So here n is minus half. So minus half plus 1 is nothing but plus half, isn't it? So here we will get plus half, and divided by the same increased degree. So that is divided by 1 upon 2 once again. Alright, and of course plus c, that is a constant of integration. So we have to always add constant of integration when we integrate. So this particular expression is nothing but the one which is mentioned there, that is 2 root x plus c, correct? So in this way we can integrate any algebraic function since we know the original formula. Right. Now moving on to trigonometric functions, integral of cos is sine and integral of sine is minus cos, because here we know that derivative of cos is minus sine. So therefore while integrating, the minus sign will appear. Right. Then for sec square it is tan x, and for cosec square it is minus cot x, and same for the other two, that is integral of sec x tan x is sec x, and integral of cosec x cot x is minus cosec x. So these are to be remembered and used directly in the sums of integration. Now let's see the inverse trigonometric functions. Now for 1 upon root of 1 minus x square, the integral is sine inverse of x plus c. Now instead of positive, if we have the negative term to be integrated on left hand side, then the integral becomes cos inverse x. So we can remember basically in pairs, that is the next two are tan inverse and cot inverse. You can see that on left hand side also we have the two similar expressions except their sign, and the last two are also very much similar, which are for sec inverse x and cosec inverse x. So these are the standard results. Now let's see another topic, that is a small topic of algebra of integrals. Here if we want to integrate sum or a difference of two functions, say f of x and g of x, then that is equal to sum or a difference of the corresponding integrals, right? So that is a pretty straightforward result to remember. And in the second result what we have is suppose k is some constant, some real constant which is multiplying a function f of x, and we want to integrate this whole product, then we can take k outside the integral and integrate only the function, which is very much similar to what we do while differentiation. If there is a constant multiplier, then we take it outside the process. Now based on this we will solve couple of simple examples.